Always good to remind people if you want it recorded. Um, okay, so I'm going to share the PowerPoint and then we can just talk about it. So this is the lecture, and yes, I need to update my. So that wasn't the one that you were talking about? Not that
No.
no? Okay.
Yeah, go further.
Oops.
This one.
This one.
Yeah.
Oh, okay. Um, so you have three equations of equilibrium, right?
Mhm.
You've got that. So the first thing to recognize, and I think in a sample problem like this, which is from the textbook, um, how much force is required of the quadriceps, so you know you're actually trying to find muscle force. So that gives you an idea right there how you're going to draw your free body diagram. Is required by the quadriceps to maintain the leg in a horizontal position. And if I have to say something, the important word there is maintain. Because maintain tells you right away that you're in an equilibrium position. Maintaining, like if I'm doing any kind of scenario where I'm holding a joint against gravity, a load against gravity, or pushing on a machine, or something like that, and I'm maintaining the posture, that means I'm not moving. So if I'm maintaining the posture, then I can use equilibrium, because of course equilibrium means there's no accelerations, and therefore the sum of the forces in the x direction equals zero, the sum of the forces in the y direction equals zero, and the sum of the torques around any point in the system equals zero. In other scenarios where it's active, you can't always use the sum of the forces around any point, but you can in an equilibrium position. So you're good to go there. So one of the things you're going to look for is something that says that, maintain. I don't know why I ended up with let's undo that. So we know we're in equilibrium because we have that word. So another key word might be something like moving slowly or something like that. So if we have a human doing some activity and we're moving slowly, we can probably use, that's kind of what we call quasi-static, because the accelerations will be so slow that we can also get away without including them. But this one we know, it says maintain. Maintain means I'm holding it in position. So right there, as soon as you're trying to find what's happening in a specific muscle, or the forces at the joint, which is part B, and you've got the code words for equilibrium, you can use those three equations. So there you've got equations. In those situations, so here's the sample, or the very first thing you're going to want to do is draw it. And I mean, you were given this in the textbook. Sometimes you have to use the words to make this drawing. It's not always given to you, but always try and draw the situation. So if you're doing a joint level equilibrium problem, you know that you're going to draw just a body segment, not you're going to chop through the joint, and you're going to draw a body segment. It says that you're holding the leg out horizontally. So there you go. I'm holding the leg out horizontally, or the calf and foot. You know that there's a weight here on the ankle, so you're going to draw the force due to gravity of the weight at the ankle. And it's lucky because this is horizontal. There's 90 degrees between the weight and the leg, which means the distance out is actually going to be the moment arm. We don't have to worry about sines or coses for that load. In this particular question, it tells you ignore the effect of gravity of the calf and foot. It's not really always a valid assumption to do that. But if the question says you can assume you don't have to worry about it, then don't worry about it. You don't draw it in there, but typically you would draw the force due to gravity of the calf and foot, and just the calf and foot, nothing else. And then you always end up over here with your two joint forces, the one in the X, the one in the Y. And if it's asked you for a muscle force, you're going to draw the muscle as a force. Once you have this is the key thing you need to do to find the equations, because you can take your torques around a point. It's any point on this system. The most common place to take it is right at the joint center itself. Your two joint forces, your X and Y components of your joint forces, act right at that joint center. Therefore, you don't have to include them in your torque equation. And that means you have two forces that can create a torque around the knee. And so this right here is the basic part of your equation, and you find out the torque being created by the muscle, which is the muscle force, times 0.04 meters, which is the distance. So if you look at it, 0.04, well, Fm times sine 30 would be the same as finding the rotary component of this force. And you're basically multiplying the rotary component times its distance. Or 0.04 times sine 30 is the moment arm for the muscle, and you multiply the moment arm times the muscle force. Either way of conceptualizing it works, and you will get the exact same three things in your equation: the distance of attachment, the force of the muscle, and the sine of the angle of attachment. It is trying to rotate if you held a pencil over top of this whole leg and pinched it right there at the elbow, or sorry, elbow. We do too many things that are upper limb. At the knee, I keep saying elbow, but I mean knee. Knee, if you pinched it right there and then pushed on it in that direction, you'll see that the pencil is going to rotate counterclockwise. So there's going to be a plus in front of that. And if you do the same thing and push down on your pencil there, you're going to see it's going to rotate clockwise. So I'm going to put a negative in front of that. And again, we have the weight, it's 80 newtons, and its distance, 0.28. And that all equals 0. Once you do that, you can rearrange to find Fm, which I gathered from what you said is not what you have the problem with. It's trying to create this equation in the first place. Is that so? It's in each case, the only part of these equilibrium equations which is common between cases is the sum of torques equals 0. And then in each case, whether it's an upper limb problem or a calf and foot one, or you have to figure out everything that's going to create a torque around your joint and either add them or subtract them. So this part, yes, is unique to each situation. So you have to think of it. So what torques are being created around my joint? Does that help at all?
Actually, yeah, no, that's actually very helpful. And
Good.
so do we do the X and Y component as well?
Yes. So where you're going to use the X and Y component, almost always, but not always, but almost always, you're doing a situation where you have to find the muscle force or the muscle torque first. That's the first thing you do. And then you do the sum of forces in the X direction and sum of forces in the Y direction. Again, not always, depends on the situation, but if you see here, we have the sum of forces in the X direction. And the second part of that question was, can you please calculate these joint forces? The X and the Y component, and well, actually the total, because the total is when you combine the X and the Y. But you start with putting in the X and doing the sum of the forces in the X direction, of which case you're going to have the joint force in the X direction going one way in a positive direction, and then you're going to subtract from that the stabilizing component of this muscle force, so which is this muscle force, which we've just calculated, times cos 30, which will give you the component of this force acting towards it. So basically, when you do these sum of forces in the X and Y direction, you not only have to have the two components of your joint force, you also will have to take your muscle force and split it into two components, the rotary component and the stabilizing component. If it's fully horizontal, if it's not fully horizontal, you might have to do something that's even more, in order to switch it into X and Y. And that can get it, because then you're not using just this 30 degrees anymore. You're going to be using something that is not 30 degrees. But anyway, it is fully horizontal, so it is 30 degrees, and we're going to use that stabilizing component. And those are the only X forces in this situation. So whatever this stabilizing component is, if the muscle's pulling the bone one way, the femur is pushing on the tib, the opposite, equal and opposite, in order to not have the tib slide up. So that's what your joint force is going to be in the X direction. And Y, again, you're going to have the Y component of this muscle force. You're going to have the Y component of your joint force, and you're going to have the force of the weight, because it happens to be fully in the Y direction also. And I'm going to put this in as a plus and a minus. And you'll see I did that because that's how I drew my joint force. So joint force Y, the Y component of the muscle force, which is that rotary component, sine 30, minus 80. And you'll note that that in the end, I'm going to get a negative value. That negative value just means that as I've drawn, you don't change the direction of the arrow. You just say that the y component of the joint force is 480 newtons in an opposite direction from what I drew. So in fact, the femur is pushing down on the tib this way to prevent the tibia from shooting up, because the muscle is literally trying to pull it up and the femur has to hold it down in place. That
I have
help?
another question.
Yeah.
Do you always subtract the stabilizing component and add the rotary component? Like, how do I know that that's a plus instead and the other one was a minus? Like, how would I know that?
Okay. You know it because of this. That's why I have you draw this reference frame. This reference frame is for you to decide, to tell me what you consider positive and what you consider negative. So when you combine them, you you're starting with your sum of forces in the y direction equals 0. That's the common equation, and then you have to build the rest of the equation by looking at all of the forces that are in the y direction. In this problem, again, specific to this problem, how I've drawn this problem, and how I drew my forces. In this problem, I drew my joint force in the y direction up. I chose to do it because I don't know ahead of time which direction it is. I really don't. So I draw it in a direction, up or down. I just draw it because I know it's there. I just don't necessarily know which direction it's going to be acting. So I drew it pointing up. My muscle force, you can see, is pointing up. It's pointing in the negative direction for the x, but the y component would be, if I drew the y component, let me just draw on this. If I drew the y component, it would look something, if it allows me to draw on it, it would look something like that, right? Can you see that? That would be the rotary. Now, see, that direction is positive based on my reference frame. So when I put it into this equation of motion, I'm going to put a positive in front of this guy. It's implied. I'm going to put a positive, which is this joint force. I'm going to put a positive in front of the muscle component because it's pointing up. And then I'm going to put a negative in front of the 80 because it's pointing down, which I would consider from my reference frame to be negative.
Okay, that makes sense.
Good. Any other questions on that?
By the way, this was so helpful. I was so confused for so long, but now it makes so much sense. So thank you.
Oh, you're welcome. I'm glad it's helpful. I always think working them together helps, but okay, let me stop sharing and we will close that guy just because. Not saving my changes. Okay. Any other questions?
Okay, so I have a question. I actually have a couple of questions. So for chapter 10, additional problem, question 6, when I was doing it, I did not convert the 50-yard to.
And you probably didn't get the right answer.
Well, of course not. Yeah, but I'm just really confused with the 50-yard thing though, because when I looked at the solution, I was just really confused. What's happening?
Well, I mean, you will get something that's pretty close because, of course, a yard and a meter are similar. They're not exactly the same, but they are similar. So the reality is that we have to let's share away here. And I will tell you right now, I will not have anything on your exam where you have to convert. It's the only problem in the book where you have to convert, only because football is done with meters, right?
That's right.
So if you have the, why is that not? Let's just draw on it. So if you have the one player who is going along the sidelines, so you've got your actual field, right? And then you have the end zone. And you have your other player who is starting here and coming down here. And they have to meet before the end zone, right?
Okay.
If in football, you don't want your opponent to cross into the end zone, or they're going to score. I don't know how much you know about
No,
football.
but yeah, that's the basic idea.
That's the goal. You've got the two teams, one team's trying to get it into the end zone, the other team is trying to prevent them from getting it into the end zone. And quite frankly, if they meet right at the end zone, it's probably too late, which is why it has to be faster than, not just at that speed. But that is absolutely the last place you can meet before they go into the end zone and score the touchdown. So in order to get a velocity, you need a distance and a time. If I recall, it gives you the time for the one guy, doesn't it? Or the speed. And let me just look it back up again so that we are...
Oh, no, there's no time given in that question.
There's a speed, though, given for one guy, isn't there?
Yes.
Yes.
The meter, the distance.
Which allows you to calculate the time. So, you can find the distance. You need the distance for the Dallas. That's the Buffalo Bill. Here's your distance for your Buffalo Bill, and this is your distance for your Dallas Cowboy. And you're given a velocity for your Dallas Cowboy, which is 8 meters per second. And that's why I often have you put, if you see me solve a problem, you'll see me put units in, even when I'm plugging them in, because we need to find, basically in the same time it takes for this Dallas to do, this Dallas Cowboy to run that distance, the Bill needs to run that distance. So you need to find the time. So time is going to equal velocity time divided by distance, right? Is that right? No. Yes. I take that back. My brain is clearly not fully in yet. That is not. So let's just rearrange. So velocity equals distance over.
Excuse me, I think it's opposite.
Time equals distance over velocity. I had it upside down.
Yes.
And again, as soon as I would have done it, I would have gone, whoa, I have it over time instead of time itself. So again, so if I had it in yards, because it's 50 yards, divided by meters per second, my seconds are going to come up here. And I would expect my meters and my meters and my yards are not going to cancel. They have to be in the same unit in order to cancel so that you're left with only time. Okay, does that make sense?
Yes.
So this one of these, either I have to change my speed to yards per second, or I have to change my distance to meters. And that's the easier thing to do, is to change the yards to meters. And you can either plug that if you don't want to think about it. There's all sorts of conversion things in the on your phone, but and there's also, you can look up the conversion factor. They give you meters to feet, so you actually have to multiply that by 3, because there's 3 yards or 3 feet in a yard. I don't know how comfortable you guys are even with yards.
I'm not.
Well, so there's 3 feet in a yard. So you have to take what they give you, which is meters to feet in the textbook, or again, look it up online, or even plug in the numbers, because again, that is not something I'm going to test you on.
Okay.
Know that a yardstick is slightly shorter than a meter stick, slightly. So whatever value you're going to get is going to be smaller than 50 yards. So 50-yard line that's how far they're going to travel, is 50 yards, which is, I believe, for off the top of my head from doing this problem over the years, it's something like 44 meters.
Okay.
That's just off the top of my head, because a meter is slightly bigger.
45.72.
45.72.
Okay.
There you go. So again, you'll have slightly fewer meters than yards, because a yard is slightly bigger. And that allows you to calculate the time. And again, you're going to need to know this distance anyway in order to calculate this distance. This distance is actually given to you in meters, not yards.
Yeah.
So they clearly want you to convert the yards to meters.
Yeah. Okay. 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 I have 2 more questions.
Fair enough. We got some time.
So now this would be chapter 12, introductory problem number 6. So my approach for that was using essentially the momentum formula. I know we didn't do momentum as far as I know. But what confuses me is that in the answer that they've provided, I mean, I still came to the conclusion that lineman B will push lineman A, but I didn't calculate velocity. But
again, for this course, knowing which one is pushing which is fair, because we don't really get enough time to do. I would love to do more collision type of questions. Okay, so I mean, you have 2 really, you have a momentum question, right? Which is, so the lineman A has a momentum equals mass times velocity, which equals 100 kilograms times 4 meters per second, or 400 kilogram meters per second. Really, this is about as far as where we'd go for B. So this is A 100. Oh, sorry. 90 kilograms. 90 kilograms times
It'll be,
4.5.
oh no, sorry, it's 405. So 405. Sorry, I shouldn't have worded that. So it would be, okay, I'm just gonna double check.
4.05.
No, it's 405. Yes.
Kilogram. So the person B is going to push A. The main piece for you to understand here is the one that has the bigger momentum wins.
That's right. But then they calculated velocity, so that's where it confuses me. Then how?
We didn't spend a lot of time on this, but if these two come together, again, we didn't do this, so you don't have to know this, but essentially, if this person so MA is going to equal, assuming they take the momentum of the other person, you're going to have 405 minus 400, that 0.03. Oh, which will be the total velocity, or the total momentum, sorry, A plus B, because they're going to be attached now. So it's going to be 5, which is 5 kilogram meters per second, but the mass is now 190 kilograms. So if you divide that 5 kilograms by the 190, or 5 kilogram meters per second by the 190, you should come up with the 0.03 meters per second. Again, I say this so you can see how it's done. So now the new velocity of A plus B is going to be 5 divided by 190. And the kilograms are going to cancel, and you'll be left with meters per second. Fair enough?
Yes, got it. Thank you.
That's what's happening there. But we never got into collision. We did this. What is the momentum of a linear system? It's kilogram meters, mass times velocity. But we didn't talk about collision.
Okay. Okay, so one last question would be chapter 13 in introductory problem number 9. I'm more specifically confused with, they're asking about the magnitude of the reaction. And the reason for that is not, because in the answer they provided that the R is equal by, the answer, and I'm not understanding why. Anyways, sorry, I'm just going off.
So number 9, you want to know how they got R?
Sure. Okay.
Is it? I'm not sure if that's what you're asking me.
I'm just confused about the magnitudes of reaction, like how.
Well, if something's sitting here, so think about this. This is a box.
Okay.
This is the free body diagram of the box.
Okay.
And so the first thing we're going to do is put the weight of the box in, right?
Yes.
And what is weight of box? Weight box is going to equal, or force due to gravity of box, depending, you can use either, that's fine. I've used both through the term, is going to equal mass times acceleration due to gravity, which is 10 kilograms, times 9.81 meters per second squared, which is going to, that's where you get 98.1 meters per second square, or sorry, newtons. Kilogram meters per second squared, which is again, of course, newtons. So that's the weight of the box. Below the box, you're going to have, and not necessarily if there is a push, there is an applied force here, so it depends where the force is applied, and that we really don't get into that until we come to equilibrium and balance. Will govern where underneath this box is. So let's just say it's here. There's going to be R, right? Over here somewhere, not necessarily directly right at the center of gravity, could be somewhere else, is your push force, which is 2 newtons. This is your applied force of 2 newtons. And then you're going to have a friction force, right?
Yes.
Again, it all comes back to that good old free body diagram. And those are what I'm going to consider positives. In this case, I really am just looking at, I'm going to really look at the sum of force equals, well, I know it's the sum of force equals mass times acceleration is Newton's second law, but again, you look for those key words that allows you to say, oh, this is a situation where we're in equilibrium. And the key word in this question is the 10 kilogram block sits motionless.
Yes.
So when it's just sitting there, even though you're pushing on it, it's not moving, right?
That's right.
So this means that's got to be 0, which means this is 0. So I both in the X and Y direction. You don't see the table or because we've replaced the table with R and the force of friction. So sum of forces in the Y direction equals 0. Let's just, as if we go back to the problem we did with the leg. Sum of forces in the Y direction. What forces that are on this free body diagram act in the Y direction?
Well, the weight and also the R.
Right. So is R positive or negative versus when you compare it to my reference frame?
Negative.
R?
Oh, whoops. Sorry.
That's okay.
Positive.
Yeah, exactly. Positive R. Is the weight negative or positive? Did I draw it in the same direction as positive Y or in the opposite direction?
In the opposite direction.
Which makes it a negative. Negative weight box. And all of that's going to equal 0 because it's not going up or down. It's stationary, not moving at all. Even if it was moving, it's probably moving straight across the table. So it's, again, not going up or down. So it still would be 0. But so once you have that, R minus weight equals 0. R equals the weight of the box, which is 98.1. And that's what they got.
that's right. Okay. Okay, thank you.
When something's sitting on a horizontal surface, and even if it's moving, even if it's sliding along that surface, it's really not moving in the y direction, right? If I'm sliding something along a horizontal surface, it's not moving up and down.
No, yeah.
So if it's sitting on a table, if it's going around a curve that's flat, or that's horizontal in nature, it doesn't have to be flat, it could be banked, but it's still you're staying at the same height. In those situations, the sum of your forces in the y direction equals 0 because you're not going up or down.
Got it.
Which pretty much means the weight of the system is going to equal the reaction force underneath it. In most cases. Anybody else have a question on that one? Okay. Anybody else have a question?
Thank you.
No problem. You don't have any more, Tanaz? I just wanted to see if there was anybody else waiting to have a problem.
Oh no, those were the 3 ones.
Good. Any other questions?
Well, if nobody else has a question, I have another one.
Well, Amos did put his hand up, so
Okay.
Yeah, my question's more about the concept of the bike. So I imagine like 2 scenarios where someone's trying to make a turn, but they aren't leaning in. And the reason why that they would tip was because, how do you describe it?
because the centripetal force that they require to make the turn, the force that will change their direction, which is what centripetal force does, it changes their direction. The only location for that centripetal force is from the bottom of it's from the ground reaction force, right?
Mhm.
And that's going to create a torque around the center of gravity, and they will go like this.
Is it because like if I'm looking at it through the frontal angle of a bike, right?
Mhm.
There's no force of friction in that plane to make the turn. So is that why you tip?
If you're making the turn, if you're actually making the turn, let me share. If you're making the turn, so, and this isn't a proper free body diagram, but I'm feeling blue. We have actually, let's just erase that and go with the ground as the green. So that's the ground. It should be horizontal, but we'll look with it. This is the person on the bike, right? And they're going around a corner that is like that, right? If we looked from above, they would be going around that way. There is no forces, external forces acted. The only external forces that are acting on this bike, the bike and person together as one system. The only thing that can turn them, into the curve, which is going to always be in that direction, is the ground reaction force. So there's a component of the ground reaction force that's going to push them up, which is going to prevent the gravity. So they have gravity acting on them, and they have the ground reaction force acting on them. And the magnitude of the gravity is going to be the same as the magnitude of the push, because they're not going up or down. They're staying on a horizontal trajectory. So the force that's pushing up is going to be the same as the force that's pushing down. The only component that actually can act in the direction of changing the direction, again, not a proper free body diagram because I haven't taken away the ground, but there has to be something that's acting that direction on them. Again, the only place that can happen is at the tire. And yes, it's got to be always perpendicular to the direction they're turning, towards the center of the radius. That's why centripetal force is, of course, the mass times the radial acceleration. And the only thing that can create that is friction. That doesn't mean that if I was looking at the bicyclist, if I was looking at them from the side, pedals, I don't know, and then leaning onto something. Sorry, ignore that. Again, drawing, we all know, is not my, and your bike you're going to have your two wheels, right? And the pedals. So you have, if I was looking at the side, there is also going to need to be friction that is acting this way on the pedals to allow me to, speed up opposite way if I was slowing down. But that's in a different plane. This is looking at them from the sagittal plane. This is looking at them from the frontal plane. So from the frontal plane, there has to be something acting sideways to the bike that's going to cause that change in the direction.
And the main reason why you are tipping if you aren't leaning in is because you don't have that force of friction in the frontal plane. Is that correct?
No. If
Oh.
you're actually making the turn, then the main reason you are tipping is because you've got your center of gravity here. If I'm not tipping, then you can see that this force, this reaction force, is going to go straight. It's going to point directly to the weight. And this weight is the weight of the whole body plus the bicycle. And you see how this R goes directly through the weight?
Mhm.
That means it will not create a torque around the center of gravity. In a dynamic situation where the force equals, where torque is going to equal I alpha, you're best to do your torques around the center of gravity, not just any point. There's reasons for that, and there's ways to correct for it, but we don't want to learn that. So it's just the sum of the torques equals I alpha, unless your I is adjusted to be from somewhere else. So if you're just looking at your moment of inertia around the center of gravity, then you're going to take your torques around the center of gravity. And so if R is pushing directly up towards the center of gravity, which it will be if you're perfectly upright, if you are perfectly upright as you go around a corner, then R is going to point directly into the center of gravity, and there's not going to be any torque, right? It's not going to cause a torque. However, if you are actually going around this corner, you need to have this centripetal force. This centripetal force must be there for you to go around the corner. Okay? It must be there for you to go around the corner. So you are going, and you can see that there is a moment arm between this centripetal force and the center of gravity. There is a moment arm. So if you have a force and a moment arm, it's going to create a torque. So the R is not going to create a torque because it has no moment arm. The centripetal force is going to create a torque because it has a moment arm. And therefore, there is going to be a torque around the center of gravity, which it will be acting in this direction, right? And if you have a torque, and it's on there for a time, you're going to have some angular momentum. Remember, because torque times time is the impulse that is going to change your angular momentum. I times that. And therefore, since your I isn't going to change, your angular velocity is going to change, and you're going to start rotating in that direction, which is usually not a good direction to rotate on if you're on a bike. You're going to fall. And I have to say, just from a purely practical perspective, my grandson, 3.5, and it just amazed me, but because of what he's had access to, but he learned to ride a bike, a 2-wheel without training wheels in the last month. And he just picked it up and started going, and straight ahead worked really well, but they had to work a bit on going around corners. Because you have to lean in a bit. If you want to go around a corner fast, particularly because, of course, this centripetal force is going to get bigger the faster you go around the corner, right? Does that help at all, Amos?
Yeah, it's just because you said that you would tip because you have a centripetal force, and the way I see it is that there's nothing to counterbalance, assuming that you're not leaning in, if that makes sense.
Exactly. By leaning in, this R is no longer pointing directly at the center of gravity. It's creating a torque that's acting in this direction. And then they cancel each other out. And that's what leaning in does. It creates a second torque in the opposite direction because this guy, the reaction force is no longer pointing directly at the center of gravity. So what we do, and we probably are fully not aware that we're doing it, if we're going around a curve, we slow down because, of course, the AR equals V squared over R. So the lower V is, the smaller AR is, which means the less centripetal force we need. And the lower the centripetal force we need, the less that torque is, and therefore we really don't need much to counterbalance the torque. Or we take a really big curve, which makes the R bigger, which again will act to to minimize that radial acceleration and therefore minimize the centripetal force. And therefore we only tip over just a little bit and it doesn't feel that far off. But it's particularly noticeable if you're going fast or you're going on a tight curve. Does that help?
Yeah, that clarifies everything. Thank you.
You're welcome. Anybody else have a question on this before I erase it all? Okay. Stop sharing. Somebody had a question before. They started to ask it and Amos got in there first. No longer there anymore? Okay, anybody have a question? I have to say, if you keep seeing me looking up, I have a bank of windows in my office that look out, and for some reason in the last 3 days I have a bird that keeps crashing into the window and flying against the window, so which I've never had before. I either am going to have to put one of those silhouettes of a hawk or something on here or what. I don't know why. You'd think after the first time that they hit it, they'd learn. Any questions? Yeah.
I have a question. So you made an announcement last night about midterm 2 reviewing.
Oh, yes.
And I couldn't find any link for that.
Very good point. It is open now.
Okay. Thank you.
I think. Maybe not.
I'll check.
It's no, it isn't.
No, I don't think so.
Now it is. Yes. It's
Let me check.
It's at the bottom of the first section.
Yes.
Yeah.
Now it's here.
Yeah.
Thank you.
You're welcome. I don't know what that bird wants, but sorry, folks. It's very distracting. Any other questions? All good? Okay, good. I'm going to stop the record then.